All right, so we're going to carry on with integration tonight. I'm not sure if you can hear it out there, but it's raining like you wouldn't believe it. So anyway, we're now ready for section 4.3, and this is more of a theoretical discussion. We're going to introduce what we mean by definite integration. So there's really two basic types of integration that we might encounter, and they're called definite and indefinite. Let me just mention those right here. And by the way, up to this point, everything we've done was indefinite integration. Definite integration means that we're looking for a specific constant as opposed to a function. Okay, so we'll see when we start working on it, but what we're looking for is a very specific number, a solution to what we're looking for, which is, or it could be interpreted as the area under a curve. So now we're going to introduce the concept of Riemann sums. Now, what's changing here is that we're making our approach from the previous section a little bit more general. So you notice how we have a function here, which happens to be f of x equals the square root of x. We're interested in the area under that curve between 0 and 1. And we've seen this before. What's changed now is that if you notice, if you look closely at these rectangles, they don't all have the same base like they did in the previous section. Okay, so in other words, it turns out they don't have to, as long as we understand the formula that determines the width or the base of these rectangles, then we can still go ahead and calculate our sums, but it's going to be a little bit more challenging. So here, for example, we're going to have the formulas. We're going to have 1 over n squared, 2 squared over n squared, all the way up to n minus 1 squared over n squared, all the way up to 1. So this way we can determine n is the number of intervals that we choose to use. And that's how we'll determine the widths of these rectangles. And if you notice, they keep getting wider and wider as we go get closer and closer to 1. So the formula is being written here as C. So by the way, what we're actually trying to solve for is here. Okay. So it's the limit of the function evaluated at CI. Now, CI, if you remember, is some constant within each interval. It doesn't have to be the center, but it has to be in each interval. So within each interval, we'll calculate the value of the function at CI and multiply it by delta x. But if you notice, if you look at it very carefully, unlike the last section, you make it just a little bigger, you can see before we were using delta x because it was a constant, okay? And you might remember that it was b minus a over n, okay, when we're assuming that it's the same base for every rectangle. But now all of a sudden it can be different. And so the way we indicate that is this I, the index I. So in other words, it's keeping track of the number of rectangles. I is the rectangle that we're looking at. And so it ranges from 1 to n. And so n is the number of rectangles that we choose to have under the curve. And so in order to calculate the areas of these rectangles, we need the height. This is actually the height of each rectangle. And this is the base. We multiply them together, add them up, and there is a result. And of course, you know, you can see here by this graph, if the bases are very wide like they are here of these rectangles, then the area of the rectangles will be, in this example at least, quite a bit greater than the actual area under the curve. So what's happening here is that as we allow the number of rectangles to converge to infinity, the sum will converge to the correct value. In other words, it'll actually match up with the area under this curve, which is shaded in purple. All right, so CI in this case, we've chosen to define our C's as I squared over n squared. And the function itself is the square root of x. Okay, so now the way this thing has been set up, each left endpoint for the ith interval or rectangle is I minus 1 squared over n squared. So remember, that means that, like, for the first one, we have this interval, and then the next one is 1 over n squared to 2 squared. And then the third interval would be 3 squared. Sorry, 2 squared over n squared. And that goes all the way up to 3 squared over n squared. And then we go to 3 squared over n squared up to 4. And then finally, in the last case, 4 squared over n squared up to 5 squared over n squared. And that's because we chose to have 5 intervals or rectangles. Okay. So the deltas can then be expressed as, now, of course, this is the difference between the two endpoints, which, because of the way we defined it, it's going to be I squared over n. Actually, what I should have done is put this here. So notice for each one of these rectangles or intervals, we're going from I minus 1 squared over n squared up to I squared over n squared. Okay. So yes, anyway, that's where this formula is coming from. So we've got delta xi is the difference between the two endpoints, which no matter which one we choose, it's I squared over n squared minus I minus 1 squared over n squared. And then, they did a little algebra here and reduced it to 2i minus 1 over n squared. Okay. So these are the i's, by the way. And then we can take the limit. Now, again, what we're actually trying to solve for is this. So we have a formula for delta xi, and we have a formula for ci. All right, so the ci we defined is here, I squared over n squared. Delta xi. Now, because the function is the square root of x, this reduces to I over n. So in other words, what you're looking for is the limit as n goes to infinity of So now what do we do with that? Well, as it turns out, by doing a little algebra, you can see that we're factoring out n cubed because n is a constant, remember. So that leaves us with I times 2i squared minus I. Now, remember, we had those formulas in the last section. Let me go open that up again because I should have kept them open, but I didn't. That wonderful set of formulas. Well, actually, I think it was this section. All right, hold on. Let me scroll back. I seem to remember it was slide number 9. Oh, no, no, I was right the first time. It's in the previous section. Which I don't think is open. Oh, here it is. Okay. Here we go. This is what I was looking for. So the sum of the i's of just I is here. And the sum of I squared is here. So that means what we have here now is the 1 over n cubed limit. So the first one will be 2 times n plus 1, 2n plus 1 over 6. And the sum of the i's is n plus 1 over 2. All right. Well, now what? They do all the they go through all the algebra. And so after you combine all these terms, you can see at the end here we have the limit as n goes to infinity. Actually, let me just copy this whole thing. So they took what we have and then they algebraically reduced it to this. Now you can actually take the limit, okay? Because you can rewrite this as they're showing here. And you can rewrite it as all right, then we can simplify it a little. Now, this first one is just 4 over 6, which is 2/3. The second one is no, sorry, it's 1 over n, 1/2, sorry, 1 over 2n. And this last one will be 1 over 6n squared. Now, remember from a previous section that when you have a limit as n goes to infinity, or x, for whatever the variable happens to be, where the x is in the denominator, this one goes to 0, and this one goes to 0, so we're left with 2/3. And so in other words, what we just did was we found the actual area, this purple region has a total area of 2/3. Now, we're not going to go through all those steps every time we do one of these problems. What we're doing here is, maybe it isn't obvious, but we're calculating a definite integral because we're looking for a specific value. And so we're going to learn techniques for doing this directly using the rules of integration, but it's nice to see where all this is coming from. In other words, this is how a definite integral is solved for. It's actually a limit. And it's a limit as you keep shrinking up the widths of those rectangles. And so, but here it's designed to give us a specific constant as a result, not a function. Okay. But by the way, if you notice, we don't have that plus c at the end with a definite integral. We don't need it because we have the constant that we're looking for. All right. Yes, so it's 2/3. So basically, what they're telling us here now is that if you take any interval and break it up into pieces like we did with that specific formula, in such a way that C is guaranteed to be between the two endpoints, then this sum that we just calculated and took the limit of is called a Riemann sum. Now, obviously, that was named after a mathematician named Riemann. And the way we divide the bases of these rectangles, the specific formula we use, it's referred to as a partition. Because we could take the same interval and break it up in many different ways. All right. But no matter how we do that, the integral itself will always give us the same results. Now here they're introducing a new concept. This is the idea of the norm, it's called. This is something that you might see in linear algebra if you get to that point, where the norm here is basically, think of it as of all the intervals that you're using to calculate your definite integral, the largest of them all, the widest one, is considered to be the norm. In other words, the norm is the width of the largest interval under the curve. So this is the standard notation. You don't see this very often, the double bars. It looks like the absolute value, but twice. So remember when we had constant widths in the previous section, this is what we had. Okay, we had a constant delta x, which equals b minus a over n. But now, that's not the case. So what they're telling us here is that the norm, the way it's defined, is if I rearrange this algebraically, just cross multiply, and in turn, so because the norm is the largest triangle, well, the largest change, the largest delta, that indicates that n must be greater than or equal to this ratio. And as the norm approaches zero, as you can imagine, the number of subintervals or rectangles approaches infinity. All right, now looks like we're getting ready to actually calculate definite intervals using the rules of integration. And so the notation that we'll use is this. So in other words, this is the heart and soul of what we're about to do. Given some curve that we're interested in studying and some partition that we've chosen, in other words, some way of breaking up the interval into rectangles, the limit as the norm goes to zero, which is the same as saying that n goes to infinity, is going to give us our definite integral, as we just saw a few minutes ago when we solved for it and got 2/3. And if you notice, the notation is a little bit different. We didn't have this before. We have these two limits of integration, as they're called. This is the lower limit of integration. And then, of course, that means this must be the upper limit of integration. So in other words, what you have to visualize here is that what you're looking for is this. So that shaded region is our definite, is that area is what we're looking for. The definite integral will give us that area. So the question is, how do we solve for it? Using the rules of integration. All right. Now, of course, we're making assumptions like we always are. We're assuming that the function is continuous over that closed interval, which implies that we can find an integral over that same interval. In other words, being continuous implies that it is possible to find an integral So what they're following the same approach we had a couple of minutes ago. They're taking the function 2x. All right, let's draw this. And they're interested in the limits are -2 and 1. So the question is, how do we solve for this? All right, so that shaded region is what we're actually looking for here. So once again, we're going to use this approach. We're going to take the limit. First, though, we have to define, yeah, okay, so we're going to use this approach. We're going to use constant bases. We can still do that. We don't have to have them all be different. We're going to use b over a minus b minus a over n. And then we'll let C be wherever we are, A is the left endpoint. We're going to start with the left endpoint and then add I plus delta x. And because delta x is 3 over n, by the way, don't forget this is A and this is B. So that means we have B minus minus 2. So that's why we have, sorry, we have 1 minus minus 2. And that means we have 3 over n. So this is the formula for CI. And now we can take our limit. Let's take a look at this. Let's follow along their logic. So again, here's how we proceed. We are taking the limit as the size of the norm, which in this case, they're all the same. So it's just delta x, which is going to 0, which means the number of intervals is going to infinity with f of ci. So ci, as we see, is -2 plus 3i over n. And since f of x is 2x, f of ci is simply 2 times -2 plus 3i over n. That gets multiplied by delta xi, which, let me copy that from up there, 3 over n. So we plug all that in and rearrange it algebraically. And now, when we take the limit, then we got a few more steps to go through. Anyway, so if you follow through the steps, and you can see we do have, here's a constant. This becomes n, just n. So this becomes -2n. And then here we have I. That gets plugged in over here. We still have the 3n. And anyway, when we get down to this point, you can see that we ultimately wind up with -12 plus 9 over n. And then this one goes to 0. And finally, when we're finally done, when the dust settles, we have -3. Now, here's the strange thing about this. the area is -3. How did that happen? How can an area be negative? Well, because most of this shaded region is underneath the horizontal axis in the third quadrant, where both x and y are negative. So um, if you were to actually calculate these areas as triangles, we'll call this, let's say, think of this as triangle 1. The area is 1/2 of the base times the height. And oh, sorry, the base, I got it backwards. The base is -2. This is the base. The height is -4. And then up here, triangle 2, let's call it. Base is 1. The height is 2. Okay. So because the area under the horizontal axis is being treated as a negative value, that's how this is happening. So you could think of this total area as -4 plus 1, which is -3. So in other words, yeah, that's why it might look strange, and that's why, because you have an area of 4 under the curve, which technically is has an area of -4, and then the triangle number 2 actually has an area of +1, so they add up to -3. So that when you take an integral like that, you're going to end up with -3. Now they're pointing out here that that isn't -3 is not the actual area. Um, what you'll actually want, what you're really looking for, is the absolute value of the two sections, the two triangles. So if that's what you're after, I mean, the actual area is actually 5 because it's 4 plus 1. But when you calculate it with this approach, you're going to end up with negatives for anything that's under the horizontal axis. So we'll see how to get around that later on. So this is the general expression for definite integral. So they want us to try this one. Maybe, no, they don't, huh? All right, well, let's look at these examples. So we start out with this one. Now, this one should be very straightforward because it's 4, which is a constant. We're going to integrate it over the interval from 1 to 3. So this is what we're looking for. The height is 4 everywhere because it's a constant. So the area of the rectangle, as you can see, is 8. And that's the end of it. I mean, that's how, so in other words, the base is b minus a. The height is 4 because that's the function. And so their product is the area, and that is what we're looking for, 8. And so the shaded region is 8. Okay. Now here's something we haven't thought about in a long time, a trapezoid. Wow, look at that, a trapezoid. So if you notice, 2 of the sides are parallel to each other. The other 2 are not. So you can think of this as, if you remember, the area of the trapezoid is 1/2 of the average of the 2 bases times the height. So that's where this is coming from. So in other words, because this is being defined over the range from 0 to 3, We have 3 here. The average now, if you notice between these two endpoints, here we have 2 and here we have 5. And so that's where that's coming from. And that ends up ultimately giving us 21/2. This is a semicircle. Now, the area of a circle is pi r squared. But we're only looking at half of it. That's where that 1/2 is coming from. And so the radius is here. The diameter goes all the way across. That would be 4, but this is the radius. So it actually ends up being 1/2 pi 2 squared, which is 2 pi. All right. Now they still haven't given us any actual examples where we're using the rules of integration. That's coming up soon enough. So they want us to notice a couple of key details here, though. Given the lower and upper limits of integration, if the two of them are equal to each other, then you have 0. Okay. Because what you basically have is a rectangle with a base of 0. Okay. So that's why the whole area has to be 0. Here, now this is an interesting result. Although it looks like there's a typo here. It should be B to A. So in other words, when you reverse the limits of integration, you have to multiply by -1. All right, what else do you need to know to do this? Well, this was a trick question. You can see that the lower and upper limits are both pi, so this is just 0. Here we go. So this is interesting. Remember before, this one, we discovered using geometry, basically, that the area is 21/2. Because we have, let's see, maybe I can copy this graph. Yes. It's not so easy to draw some of these graphs. So any help, I am very pleased. So what they're asking us to do now is basically look at what it would look like if we're flipped upside down underneath the horizontal axis. So in other words, we don't have to do any work. It's just the negative of the first case. All right. Now also here, they want us to see that you can actually take an integral and break it up into 2 smaller integrals. If you look carefully at the limits of integration. Now, of course, the motivation for doing this is you might be able to split it up into 2 simpler integrals and make it easier to solve for. So if you notice, it starts as A to B, and then we break it up A to C and C to B. These have to be the same. Okay. So this is what they're asking us to do. Let's look at this for a second. So the function is here, and the integral from A to B could be subdivided into the area between A and C over here, and then between C and B, and then we just add them up. So again, you wouldn't normally bother to do that unless that helps you simplify the integral that you're looking for. Now here's an interesting one, because this is the absolute value of x, of course. And remember, the way that absolute value is formally defined is and the way we draw it, so that's what we're looking for. And of course, you've got two triangles here. So the area of this triangle is 1/2 base times height, a half times 1, which is a half. And of course, these are mirror images of each other, so that must be true in both cases. So you get a half plus a half equals 1. Okay, so you notice they split it up into two separate pieces, each of which is extremely easy to integrate. Integrating an absolute value, I'm not sure if there's any formulas for that. So they're saying, well, don't worry about it. Break it up into two pieces, the positive region and the negative region, and integrate them separately and then add them up. So it's a perfect example of how this approach can simplify our results. All right, what else do they have for us? Oh, some general rules, some more general rules. This one just reminds us that you can factor out a constant. That was true for the indefinite integrals as well. You might remember, for example, that's all that it means. And then we can add and subtract. That was also true with indefinite integrals. Ah, so yeah, here's what they want us to do. Split it up into 3 parts. Factor out the constants. And then, so what they're doing here, they haven't yet, they're not quite ready to show us how to actually solve for these definite integrals. So what they're doing instead is they're saying, Psst, here's the values in case you need them. So in other words, they're telling us that this is negative 26 thirds. This middle one is 4. And then at the end here, this last one is 2. So in other words, we'll see in the next section how to actually solve for those. It's really not that difficult. I'm not sure why they're waiting so long to show it to you, but that's how they want to do it. Let's see. So the integral of x squared dx, yeah, 26 thirds. The integral of x dx is 4. So we actually have 4 times 4. And then here we have 3 times 2. All right, so we have minus 26 thirds plus 10 So that's 4/3. So whatever this function is, the area underneath it is 4/3. All right. So you know what? Let's see. I think what is next? Oh, you know what? I know why they're holding on to this information. They want us to look at the fundamental theorem of calculus before we actually learn the rules. So this is 4.4. The fundamental theorem of calculus, there's actually two equivalent parts to it. This is what makes it possible to have definite integrals. Okay. So first, and like almost everything else in calculus, this was invented by Sir Isaac Newton and also Gottfried Leibniz. It's an interesting story how Newton, as you know, is one of the greatest scientists who ever lived, and he basically invented the laws of he invented calculus to help explain his laws of motion. But unknown to him, now he was, of course, he lived in England in the very late 1600s, early 1700s, unknown to him, around the same time in Germany, a mathematician named Gottfried Leibniz independently discovered a lot of what we now know as calculus as well. And so there's a bitter rivalry between the two of them over who got there first, who, they all both felt like they were the ones who invented calculus. But I think historians have decided that it was Newton maybe got there a little faster than Leibniz, but then two of them had no idea that the other was working on calculus. So a lot of the notation that we see today, some of it was taken from Newton's work and some of it was taken from Leibniz's work. That's one of the reasons why we have so many different equivalent ways of expressing the same concepts. So yeah, what they want us to do is this just a quick reminder that integration and differentiation are just inverse operations of each other. And so now this is actually the statement of the first fundamental theorem of calculus. So what does it mean? So what it's essentially saying is this. If you've got a definite integral, what you're actually doing is evaluating the resulting integral at b Remember, we're using capital F to represent integrals. Lowercase f is the original function. Evaluate the integral at b, or at x equals b. Do the same thing here with a. And then subtract them. And that's your final result. Okay. So it looks surprisingly straightforward, and it is really not very difficult. I mean, the tricky part, what I mean is, the tricky part is solving the integral itself. The rest is straightforward. So that's the first, or sometimes it's just called the fundamental theorem of calculus. Sometimes it's called the first fundamental theorem of calculus. The second one is just an equivalent way of expressing the same thing. This is the one that we'll be using all the time. Oh, no, that's not it either. All right, here we go. Oh, and yes, they mentioned it again. I think I mentioned earlier, when you're solving for a definite integral, we don't need the constant. Okay, so that's one of the differences between definite and indefinite integrals. All right, so, we finally get a chance to practice with the actual rules of integration. This is good. All right. So I think you'll agree when you see these are not very difficult. It's a very straightforward idea. So here's what we're going to do. We first treat this as if it were an indefinite integral, and then we solve for the actual numerical value. So in other words, we're going to write it like this. And we certainly know how to do this. So notationally, because we're trying to evaluate this between these two endpoints, we're going to, not every book does it this way, but we're going to write it like this. And what does that mean? That means you're going to evaluate this function at 2, and then at 1, and then solve for the difference between them. Now, keep in mind, this is A and this is B. So what you actually have here, this is f of x. This is f of A, B rather, and this is f of A. Over here, we have okay, so this is our f of x for this case. This is f of B, and this is f of A. Oh, is that all there is to it? Yes, it is. So you have 8/3 minus 1/3 over here. Ah, that's all there is to it. So compared to taking all those limits and all those formulas, wow, this is really quite down to earth, isn't it? All right, so let's try the second one. Now, for something like this, we really should clean it up a little. That constant in the denominator can be factored out of that expression. And so what we're going to do now is solve for this as 4 3/2 1 minus 1 to the 3/2 power. Now 4 raised to the 3/2 power, what you're basically doing is you're taking the square root of 4 and then you're raising the result to the 3rd power. So in other words, you have 2 cubed, which is 8. And you ultimately end up with 14. All right. So one more. Well, we have trig functions. So remember, I did post that list of basic trig functions, trig integrals rather. Actually, let me go get that thing open again. Not the integration tables. That's the full-blown one from the book. This is the basic rules of integration. It's bound to be in here somewhere. There it is. So the integral of secant squared of u is tangent u So we'll solve for it as tangent pi over 4 minus the tangent of 0. Okay, I will double check my calculator. This is 1. And this is 0. Excellent. So we just end up with 1. And so that's how you calculate definite integrals. So you can see it's not much of a stretch compared to what we were doing before. Okay, it's just that now, like I said, we're looking for a specific constant instead of a function. And we also don't need the constants anymore. All right. Now, let's see. All right, so the mean value theorem applies to integrals. Basically, what it's telling us is that if you're looking for the area under a curve, there's a point in that interval somewhere such that the rectangle circumscribed around it equals the average area. Is the total area under that curve. In other words, here's the C. If I define a rectangle based on C and the two endpoints, that shaded this here equals the entire area under the curve. The question is really finding that C at which this is true, but we know that it exists based on the mean value theorem. Okay, now we saw this once before, the mean value theorem. It basically was telling us that, we've got some interval A to B, you calculate the slope of a secant line through those 2 points. You're guaranteed that somewhere in here, there's a point C such that the tangent at that point has the same slope as the secant line. So with integrals, it's opening the way to give us a simpler way of calculating the areas under the curve. Okay, but of course that means we have to look for the C. So, but anyway, now the average value over a given interval is very simply the definite integral from A to B divided by 1 minus B over A. So it's very straightforward. Let's copy that here. Let's see. Average value of a function on an interval, right? Okay. And of course, the interval is B, A to B, of course. Here they're basically proving it. It's based on the previous result, the mean value theorem. Here we go. Let's do an actual example. That's more fun than proving it. So they want to know what is the average value of this function on the interval 1 to 4. So basically, remember how this works. Okay, so A is 1, B is 4. So and the function is 3x squared minus 2x. All right, so we'll break it up into two pieces. All right, that should do it. Yes, that's right. Okay, so now we'll have, by the way, well, all right, let's leave this out here. So there's some cancellation available to us here. Okay, so you notice what I've done? I've solved for the integrals and then I've evaluated it at B4 and at 1, and I subtract one from the other, like we did earlier. And now we just have to sort through all the rest of it. And there we go, 16. Very good. Now, the second fundamental theorem, like I said, it's an equivalent version of the same thing. It's expressed a little bit differently. What they're doing is introducing a fairly complicated idea that one of the intervals, one of the limits of integration is not a constant, but a variable. So I think maybe we can knock it off right here, and we'll pick this up next time. This is the end of 4.4. Now, 4.5, which comes after this, is a very interesting concept. It's a technique that we can use to solve for a whole array of different kinds of integrals. You'll find that this one is very useful. You'll see it over and over and over again throughout Calc 1, Calc 2, Calc 3, or whatever. So this is really maybe the most complicated but most important rule that you'll see in Calc 1. In Calc 2, you'll spend a lot of time learning much more advanced, far more advanced integration techniques. But this will always prove to be one of the more useful ones. Okay, so the next time we meet, we'll wrap up the second fundamental theorem of calculus. We'll just briefly see what it's all about. And then we'll dive into this. This is where we're going to spend all of our time because this is so important. And it does take a little getting used to. What we're essentially doing is integrating functions that are the result of the chain rule. But anyway, I'll say no more now. We'll get back together next time and we'll go over this. Okay, so I'll see you then.